Yo, 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 McHugh crew, we're back again. We're talking about rotational kinematics today. So, this whole new unit, we're talking about rotation, and basically, it's going to be a review kind of almost every day. We're going to talk about one of the units we already did, but now we're going to rotate it. So, we started out with kinematics, so now we're going to talk about rotational kinematics. There's a lot here that you're going to have seen before, but I'm going to go over my top 5. Whoa, that was only 4. Top 5. There we go. Rotational kinematics formulas. So without any more talkity talk, let's go. First off, when we talk about rotation, rotation is anytime I have any object spin about an axis. So this would be a rotating object. It can rotate on several different axes, but since it's a wheel, we're going to use it how it was, meant to be used. Now, since we're talking about rotation, we've got to define which way a positive rotation is and which way a negative rotation is. So for that, we're going to use what we call the right hand rule. So you take your right hand. Your thumb is going to be the axis of rotation, and then you just make a kind of a thumbs up, a loose thumbs up. The positive direction is going to be where your fingers curl if your thumb's up. The negative direction is going to be where it curls if it's thumbs down. So I have 2 circles here. If this one's rotating this way, I would put my thumb in the center where the axis is, and then my fingers are curling around in the positive direction. This is a positive rotation. What is on my thumb? This one is going to be the opposite. This is going to be a negative. So I've got thumbs up for positive, thumbs down for negative. If only there were some sort of mnemonic to remember that by. So my number 5, oh geez, I'm going the wrong way. Number 5 is going to be the definition of angular position. So when we talk about angular position, we're going to talk about it in terms of theta, and that's going to be the distance that the object has rotated or rolled divided by the radius of that object. So I've got a 4 centimeter roller hockey wheel here, and I've got a roller. My roller is about 15 centimeters this way. If I have it roll 15 centimeters, we can figure out so if this angular position, this dot here started out at 0, we can figure out where it is now by doing the distance, 15 divided by 4. So 15 divided by 4, you should come up with, so theta is 15 over 4, you should get about 3.75. So the units for angular position are radians. 2 pi radians equals 1 rotation. We're a little bit over 1 pi here. We've rotated a little bit more than halfway around this circle. So everything's going great. Good. That's nice. Now, if we're talking about a position, a change in position would be a displacement, right? And that's where we get our angular displacement formula. Ooh, but angular displacement didn't make the top 5. But basically, it's your final theta minus your initial theta is your angular displacement. So if we started with a theta 0 and we rotated it through to 3.75, that'd be 3.75 minus 0. Now if I did another 15, so now I'm up to 30. Now I could do 3.75, or its position here, minus the 3.75, and I would find that I want another 3.75. Okay? So, number 4 is the definition of angular velocity. So, angular velocity is going to be how fast it's spinning. We should have guessed that. So, angular velocity, once again, we ran out of Latin letters a long time ago. We've got this this letter, or this number 3 that fell over. That's omega. I guess it could be a crude doodle if you know. Anyways, so we've got delta theta over delta t, and the units are radians per second. So, for an object in constant motion, we can rewrite that to come up with theta f, the final angular position, is equal to the initial angular position plus the angular velocity times the time. So if I'm spinning this at a constant velocity, then I would know, like, after 2 seconds, if my angular velocity is 2 radians per second, after 2 seconds, I would be going 4 radians. So I would have rotated through 4 radians. If I was kept rotating for another second, so now it's a total of 3 seconds, so delta t would be 3, then I would have 6 radians. I'd almost be all the way around one time. So, oh, hey. Now, if you remember way back when, if we had a constant motion, xf, the final position, was equal to the initial position plus how fast we were going times the time. So where we end up is equal to where we started plus the velocity times time. We're going to see this a lot with rotational kinematics. So moving on then to number, I don't want to give away too much here. Number 1 might surprise you. Angular acceleration. So if we've got a velocity, we've got an acceleration. Now, AP Physics 1, AP Physics C, we're going to stop at angular acceleration. We're not going to go any further. But if you really wanted to, you could define an angular jerk and an angular jounce. That would just be crazy, though. I've never actually heard somebody say angular jerk until it just popped into my mind right now, but I'm sure somebody has. Anyways, so for angular acceleration, we're going to use the Greek letter alpha. So we've gone from omega to alpha. Change in omega over change in time, and we're going to have radians are going to be seconds squared. So this should look a whole lot like our first definition for acceleration, for translational acceleration. A is equal to delta v over delta t. And that's pretty much how it's used. So if I have a spinning object, right, and then I just slow it down briefly, I'd be able to figure out its acceleration. Or if I spin it and speed it up, I can figure out that acceleration by the change in angular velocities over time. So, likewise, number 2 is going to be, what's that look like? I know what that looks like to me. We've got our final angular velocity is equal to our initial angular velocity plus angular acceleration delta t. That is our how fast rotational formula. So we had our how fast translational formula. We never called our how fast translational formula because why would we throw in translational? It's just going to throw off all our high Qs. But our how fast translational formula was Vf is equal to V naught plus A delta t. So now we can figure out how fast something's rotating if we know its angular acceleration and how long that angular acceleration lasts. So, for instance, if I had a spinning wheel and it's spinning at 2 radians per second, and then it has an acceleration of positive 0.5 radians per second squared, and we accelerate for 10 seconds. That's just the simple plug and chug formula. So our final would just be our initial 2 plus 0.5 times 10. So this one is going to be speeding up, right? So 10 times 0.5 is going to get us 5. That would be a final angular velocity of 7 radians per second. I hope that this is kind of like, well, yeah, of course, because this is literally like, what, day 2 for us? And we're just doing it, but now we're thinking about it being a spinny motion instead of a straight motion. Okay? My number one all-time angular rotational formula for kinematics is going to be it's a how far formula for rotation. So our final position is going to be equal to our initial position plus our initial angular velocity plus our 1/2 times our angular acceleration times delta t squared, just like our how far formula from way back when. So if we were using the same values here, and let's say we had theta naught, kind of liking the big, I might just come back to school all tatted up like, oh wait, tattoo parlors are closed. So if my initial position is pi, just for fun, we could figure out what our final position is. So our final position would be theta plus W naught, it was 2, the time was 10 seconds, plus 1/2, our angular acceleration was 0.5, and then 10 seconds squared. So pi is going to be 3.14 plus 2 times 10 is 20, plus 1/2 times 5 is 0.25, 10 squared's 25, so that's going to be 25 total. So that means our final theta position would be 3.14 plus 20 is 23.14 plus 25. So that is 48.14 radians. To figure out what that would be in terms of rotations, we would just divide that by pi, and you should get, it's about 15 1/3 rotations. Now, honorable mention, didn't quite make it in, would be our squared formula, so our time-independent kinematics formula, the one that doesn't have time in it. So W squared, or no, not W, omega squared final plus omega squared initial is going to be 2 times that acceleration delta. So basically, it's the acceleration times how far we accelerate for, just like it was before, to figure out how fast we would be going at the end. And really we just get this one by combining these two. So if I didn't know this formula at all, I could just use information from this and this to solve for the same way. That's why it only gets an honorable mention. Plus, no one wants a top 6 of anything. Okie dokes. Don't forget to click like and subscribe.